Hello students, and welcome to today's lecture, which is going to be on halogens, and in particular today's lecture is going to be specifically on haloalkanes and the reactions that work with them. And this particular lecture, what we're going to be working with primarily is the idea that we have different kinds of reactions. And the different kind of reactions that we're going to have is going to start with an Sn2 reaction, okay? And an Sn2 reaction is a substitution nucleophile reaction. And the two is going to indicate there are two compounds that are involved with it here. And I want to kind of go ahead and show you guys like the main theory about what's happening when we do a Sn2 reaction, okay? So an Sn2 reaction is what's also known as a backside attack reaction. And the main thing that's going to be happening here is that we're going to have some sort of nucleophile. And this nucleophile is essentially a compound of some sort that has electrons on the outside. So this right here is an example of a cyanide ion here. And notice that it has these electrons on the outside. It's going to really want to bond to some sort of nucleus here, okay? And so what's going to happen is that when it approaches our organic molecule, especially the one that has a halogen on it, it's going to go ahead and approach it from the back side, so the side that's opposite of the halogen, and it's going to go ahead and force the electrons that are in the bond from the carbon to the hydrogen. So this bond right here, this is our main bond that we're going to be concerned with. It's going to force the electrons from the bond to go to the bromine, and it's going to go ahead and bond the carbon with the carbon of the nucleophile, okay? So this is what's going on in a typical, what's known as an Sn2 reaction, which is a substitution nucleophilic bimolecular reaction, okay? And that's why it's labeled as Sn2, okay? So we have a nucleophile, something that has electrons on the outside. It comes from the back end, and the electrons that are on the outside force the electrons in the bond between the carbon and the halogen over to the halogen, and it substitutes the new nucleophile for the halogen. Okay, and so this is our basic kind of reaction that we're going to be looking at for today. All right, and here's an example. Notice that the bromine ends up getting kicked off because it is, substituted out. Okay. Now, in general, a haloalkane is going to be a compound in which we have carbons, hydrogens, and then we have at least one alkane. Okay, and the X can either be fluorine, chlorine, bromine, or iodine. Okay, we should have iodine right here as well. Okay, and the general formula is that it's going to be C to some number, H to 2N plus 1, and we're going to have one X that takes over one of the hydrogen positions there. Okay. Our reactions with the haloalkanes is mainly going to be, we're mainly going to be concerned with substitution reactions for today. And there's a couple of things that we can do to, a couple of reaction mechanisms that we want to know specifically, in particular with aqueous alkali. Okay, so aqueous alkali, this means that it's dissolved in water. And what's going to happen is when this molecule right here comes into contact with the alkali, it's going to go ahead and knock off the bromine, and we're going to go ahead and make a salt with that bromine. And the reason for this is that the alcohol, the OH group from sodium hydroxide is going to go ahead and do a nucleophilic attack. Okay? It's going to attack the back side of the carbon that has the bromine on it. Okay? Remember that this carbon is going to have a slightly positive charge because bromine is going to grab a little bit more of the electrons. Okay? The nucleophile is going to come on the back side, so I would prefer it to, if I was drawing this one out just myself, I'd have it coming from this side. It's going to cause a temporary bond between the carbon and the hydroxide. Okay? This transition state. The electron from the bond will end up going to bromine, and then it'll end up having that full bond to that hydroxide ion. Okay? So this is a way for us to go ahead and make an alcohol, okay? Because we have an OH group from a haloalkane. The next type of reaction is going to be known as a hydrolysis of haloalkanes. And hydrolysis of haloalkanes are going to be done under reflux. And what reflux is essentially a way of making sure that of adding heat to the reaction to make sure that we have enough activation energy for it to go forward without actually losing all of our products. So remember, most organic compounds are going to have a very low boiling point, and because of that, we don't want to end up losing our products to the air. So our reflux is going to be some sort of heat source. We'll have our reaction vessel here, and we'll typically have something in there that just helps with the boiling. We'll have some sort of boiling stones in there, and that just helps to make sure that the heat is evenly distributed. And we'll have our haloalkane, and then we're going to have it in a long container, and in this container we're going to go ahead and have what's known as a condenser. And the condenser, its whole point is to go ahead and cool this area of the tube to make it so that none of the organic compounds continue to boil out. So it's just to condense back down our organic compounds so that they do not leave the container or create too much pressure within the actual container. Okay, so we'll end up getting some evaporation, and then we'll have it condensing back down with this condenser. And how the condenser works is that it's essentially an envelope that holds onto water, and then you move water in. Water is going to go ahead and gain energy from the tube itself, and then the water will leave, and then you're constantly flowing cold water over it to make it nice and cool. Okay. This reaction here with the hydrolysis of haloalkanes is going to end up being very similar to the addition of sodium hydroxide. The reason that it's going to end up being the same is because you have to remember that H2O is essentially HOH, so it's still a hydroxide ion that's going there. Okay, and it just takes a little bit more energy to break apart that H ion from the OH, which is why we end up doing this under reflux. And what you'll notice is that we end up getting the same kind of alcohol group produced, and then we get H plus and Br minus. Typically, if we're going to be doing this type of reaction, we will do this reaction in the presence of silver nitrate. So we might have some silver nitrate dissolved in here. And the purpose of that is that, remember that silver nitrate is going to react with any of our halogens, and it's going to go ahead and precipitate out there. So this is a good way to test if we end up making some halogens, and hopefully we'll be able to do this experiment later as well. Okay. Next, we're going to go ahead and briefly talk about the rate of reaction. And the rate of reaction, and we're talking about both hydrolysis and substitution reactions. The rate of reaction is going to be based on the actual halogen itself. Fluorine is going to be the least reactive, okay, because fluorine's going to, just the size of fluorine is so small, and because its size is so small, it's really tightly bonded to that carbon. Therefore, it would take a lot of energy to release that fluorine from that carbon. Okay, and then chlorine is the next least reactive, followed by bromine, then iodine. And this is all has to do specifically with the size. Okay, so the smaller the size, the more tightly it bonds to carbon. The larger the size, the more weakly it bonds to carbon. And therefore, it's easier to bump off the larger molecules like iodine than it is the smaller ones like fluorine. Okay. This also, we can also do substitution reactions with cyanide ions. Okay, and this is an example where from our actual first example here. The cyanide ions also are a way for us to go ahead and do this type of substitution reaction. In general, we have to end up doing this in the presence of ethanol. The reason that has to be done in the presence of ethanol is that the OH from the water would also like to go ahead and bond and do the substitution reaction. So we have to use ethanol to dissolve our cyanide in order to make this type of substitution, because otherwise the water will go ahead and bond up there. So like a nice trap question that you can ask on a test for this would be like, hey, if you had cyanide ions, what would you dissolve them in order to do a nucleophilic reaction with halogen? And you would put, and what's your reason why? And you would end up putting that you need to dissolve it in ethanol in order to ensure that you don't end up having a nucleophilic condition with a hydroxide ion instead. Okay, this is typically the way that we add a carbon to a small chain, because this is, we're essentially adding a carbon straight to the carbon chain. So first we turn it into a halogen, and then from there we'll go ahead and add the cyanide ion under reflux. The last type of reaction would be to add ammonia to it, and the ammonia would end up being added the same way. A reminder that the ammonia in and of itself ends up having a set of lone pair electrons, and those lone pair electrons are going to be what kind of bonds in and attaches via nucleophilic addition to our main carbon molecule. Okay, that's going to be it here for our Sn2 reactions with haloalkanes. Some things that I want you guys to remember is make sure that you know for sure that the process by which an Sn2 reaction happens. Namely that we have a backside attack of the nucleophile, and that it causes the electrons to be pushed towards the bromine even further, and we get this temporary partial bond state, this temporary state, and then the electrons that's in the bond that's originally with our halogen completely move over to the halogen and make a halogen ion. All right, this will close today's lecture, and I hope that you have a wonderful day.